So hello, everyone. My name is Katie, and today I'm here with Mayank and Daksh, and we're presenting neural networks for feature analysis. So first, I'll start with our motivation to kind of explain what exactly our project is and why we're studying what we're studying. So first off, I'll explain that the most common or standard procedure of conducting animal studies is to use hypothesis testing. And basically, hypothesis testing just involves a scientist like observing some kind of behavior, coming up with a hypothesis as to like what exactly is happening, and then testing it to see, is this hypothesis correct or not? And so this is a kind of deductive method, and the issue with that is you're guessing. You're guessing like what is happening, what exactly is the pattern. And so what our solution to that is to basically ask, like, models are smarter than humans. Can we use a model to determine exactly what's happening and what the pattern is? So can we analyze features of behavior that we wouldn't expect by looking at a video alone? And our question is, how well can neural networks analyze behavioral responses to a stimuli?
So essentially, what we're going to do is we're going to create some kind of contrived example of an agent that exhibits some sort of behavioral response to a stimulus. So we don't care what the stimulus is. It could be like a magnetic field in the case of the beehive monitoring group. But in any case, the unbiased case represents no stimulus, and the biased case represents some response to a stimulus. Maybe it's like turning right. And we can quantify that amount of bias, and that represents the strength of that behavioral response. And essentially, we just take samples from the unbiased set and the biased simulation, and then we just train a neural network to distinguish between which was which. And if you get a good accuracy, that means that you did learn the behavioral response that was present in the agent. And the main question that now we ask is, how does the accuracy of a neural network that we train depend on the amount of bias that is actually present in the agent? So we use this software stack as a B analysis. It's the same one that the Beehive monitoring group used. So essentially, the way it works is you start off with some footage of some, or you generate some footage, and then you compile that into some data set, which is just a tar file. And then you use that to train a modified version of the AlexNet network, where the input is a series of frames. So the first layer of the first convolutional layer has to change accordingly to adapt to that stack of frames, essentially. And then you just report the accuracy for that bias value.
And so in the process of testing our model and training it to recognize these different behaviors, we kind of ran into an issue where we weren't getting the results that we wanted, and there was an error, and we didn't know exactly what that was. So we decided to backtrack and use unit testing. And what unit testing basically is using simpler test cases to make sure that every component of the stack is working, and that these simpler cases can allow us to move on to more complicated cases. And so we used three main basic cases to kind of train this model again. And the first one was black and white frames. So you have one class of completely black frames and one class of completely white frames. And you basically just want to test to see if this model can determine the difference between these two colors, which is a very basic test, but we need to make sure that it's correct in order to move on to more complicated things. And so the second test that we used was a left and right checkered pattern. And as you can see in the first class and the second class on the left and right, the colors are basically just inverted. And we want to see if this model can recognize the difference between these two different patterns. And lastly, we tested a clockwise versus anti-clockwise test, which Daksh will explain a little bit more about.
So the reason why we did the clockwise versus anti-clockwise test is because we wanted to see if our model can learn time-varying features. So as you can see, one of this Pac-Man is moving clockwise and the other one is moving anti-clockwise. And on applying our machine learning model with 4 frames in each sample, we were able to get 100% accuracy. And on training it in 1 frame per sample, we got a 50% accuracy. And that's what we expected, because if you just have 0 transitions, it has to purely guess. And that's why it's 50% for 1 frame. Then we moved on for a simulation for feature recognition. And the main motive behind this is to test for unexpected behaviors. So as you can see, this is a completely random motion. And after every frame, the Pac-Man deviates at any angle between -10 to +10 degrees. And this is what the bias model looks like. So in this case, whenever the rotation is towards right, it moves that amount and it adds an extra 30 degrees in this example. So we ran this simulation by varying the bias from 0 to 20 degrees. And this is the graph that we found. So as you can see in the accuracy versus bias graph, it's a S curve. And when the bias is very low, the accuracy stays around 50%, but at a higher bias, it jumps up to 90%. And the reason it doesn't increase more than that is because of the overlap cases where the transition is left, left, left. Because in that case, it will have to purely guess which class it belonged to.
So the most obvious next step that we can try to look at is to just increase the sophistication of the behavioral model. So let's say that you have some agent that is trying to reach a destination. So in the case that there is no simulation, suppose that we hypothesize that there is actually, it just like sees the destination, just kind of guns it straight towards the destination directly. But suppose that there is a stimulus, and let's say it's some sort of magnetic field. We can then hypothesize that maybe the agent will try to move in that direction of the magnetic field. And we can see that it kind of curves in this direction. So we did actually make a simulation where we placed the agent at random points. And then we actually observed that in the case that there is a stimulus or there is a bias, you can see that it kind of follows this like curved trajectory. And we wanted to see if our neural network was able to analyze that. And we did end up training like the neural network for different values of the bias, but we're not really satisfied with with how we analyze the behavioral model to begin with. So that needs a bit of more work. Maybe the next group can take care of that. And the other step that we can do is to look under the hood of what the neural network is actually doing, because we actually have no idea what the network is learning. It's like a black box. The only measure that we're really getting is the accuracy. That's the only thing that we're all we know is, okay, it's either learned something about the behavioral response, or it hasn't learned something. So then the solution is to use what are called saliency graphs. So essentially, suppose like say for example that you're trying to classify if an animal is like I don't know what that is, a cheetah or like flamingo. So the saliency graph will highlight what part of the inputs contribute most to the model, which points are the most salient. So then that'll help us understand which part of the behaviors were actually picked up by the neural network. And that's it. Thank you. Any questions?